All right, welcome to Friday week 2 already. That was pretty fast. Today in the class we're going to talk a lot about vectors and more vectors. So I think slides 1 through 11 are a really nice review of this material, so have a close look. The 10,000 foot view here is that vectors are really, they help us simplify problems. They're really nice because they help us simplify problems. When we have to subtract vectors, I like to think about it graphically. Take a look at slide 311, but there's a special trick for subtracting vectors that I like to use. So let's do an example here. I have two vectors. It doesn't matter what they are, but we'll call this vector A, and let's call this vector B. Now, I'm interested in the difference, A minus B. Now, don't forget, minus B is really plus the opposite of B. When I say the opposite of B, I mean the vector in the opposite direction. Okay? So if I want to find this difference, A minus B, what I do is I take the vector A and I add to that the opposite of B, which looks something like, that's not quite right, it looks like it's a little bit, yeah, something like this. So that's minus B. And so that difference now becomes a simple sum, and I think the sums are easier because I go from here up to here, and that's my difference, A minus B. So I think that this is a nice trick to learn. Part of the reason why we do this is so that when we add vectors together, we can find components. So in this example, working with components, we can either add the vectors up graphically, or we can find the resulting vector by looking at components. So in this vector, we have in this example, we have two vectors, A and B. We want to add them together to get vector C. Note here, graphically, we've done something similar to what I just did. We added A, tip to tail, to B, and we get this vector C. But we can also take the x component of A, add it to the x component of B, and we get the x component of C. Similarly, the y component of A plus the y component of B gives us the y component of C. Okay? And you can do this for an arbitrary number of vectors. So there are two complementary ways to think about adding vectors. Now this is particularly pertinent in our work when we start thinking about acceleration. Okay? So acceleration is the change in the velocity. So in this example here, from slide 315, we have two velocity vectors. We have a final and an initial. And in step 1 here, we redraw the final one. And if I want to find the difference between the final and the initial, I add to the final the opposite of the initial. Let me say that again. In step 2 here, I add to the final velocity vector the opposite of the initial vector. That resultant sum gives me the difference, delta V, as we see in step 3. The acceleration points in the direction of delta V. Okay? I'd have to scale it by 1 over delta t, but the point is, the acceleration points in the same direction as delta V. Now, when you're working with acceleration, don't forget, it's the change in the velocity vector, which means that the acceleration represents a change in magnitude of the velocity, a change in direction, or possibly both. Now, as we're working with uniform circular motion, keep this in mind. Uniform circular motion is really very common. It shows up everywhere. It's a really nice model. Pay close attention to slide 316 here. In this case, keep track of the velocity. What's the velocity doing? Is it changing? How is it changing? Draw a motion diagram. Try to make sense between what the velocity is doing, what the acceleration is, and make sure that your conceptual understanding matches what the vector diagram tells you. Again, have some patience,
but make sure that you sort of challenge yourself to fully understand what's going on. And make sure that you come and ask for help when things aren't clear.